In this video, we're going to be continuing with CC13, which is groups of the periodic table. Again, this is just a paper 2 topic, and this is the second video where we are going to be looking just at the halogens. The first thing we're going to be looking at is the trend in reactivity of the halogens. When we looked at the trend in reactivity of the alkali metals, we saw that the metals became more reactive as you went down the group. So as you went from lithium to sodium to potassium, they were getting more reactive. When we look at the trend in reactivity for the halogens, we're going to see the opposite. They're going to get less reactive as you go down the group. So fluorine is the most reactive, and then iodine will be the least reactive. Sorry, you've got astatine there as well, which will be the least reactive. As with the alkalis, you're going to need to be able to explain that trend. So if we remember with the alkali metals, they were all trying to lose an electron, and as you move down the group, the atoms got bigger and it became easier to lose that electron because the electron was further from the positive nucleus. With the halogens, they're trying to gain an electron. Because they're trying to gain an electron, that's harder as the elements get bigger because that attraction is getting weaker. Okay, so just like what we have with the alkalis, the atoms are getting bigger. You've got more electron shells as you go down the group. Because the atoms are getting bigger, the attraction between the nucleus and the outer shell electron is getting weaker. So those two statements are true for both groups. But with the alkalis that are trying to lose an electron, it's a good thing that that attraction is getting weaker because it makes it easier to lose the electron. But for the halogens that are trying to gain an electron, it's not helpful that that attraction is getting weaker. It makes it harder to gain an electron. So I have written that out here in words. Trend in reactivity, they're less reactive going down the group. The reason is you've got more electron shells, weaker attraction between the nucleus and the outer shell electron. It makes it harder to gain an electron. So if I were to draw here fluorine, it's in period 2, it's only got 2 shells, compared to bromine, which is in period 4 and would have 4 shells. It's much easier for fluorine to gain an electron because the electron is closer to the nucleus and will be strongly attracted to that fluorine atom. For bromine, that nucleus is quite far away from the outer shell. It makes it hard for that positive nucleus to attract a new electron. So going down the group, they get less and less reactive. We need to look at displacement reactions to prove that this trend in reactivity is correct. We look at displacement reactions. You always start out with a halogen that's by itself, and then you've also got a halogen that's part of a compound. If the halogen that's by itself is more reactive than the halogen in the compound, they are going to swap places. Using our little trend of reactivity, I can see that chlorine is more reactive than bromine. Therefore, chlorine and bromine are going to swap places. That means that bromine is going to be left by itself, and sodium is now going to be bonded to chlorine instead of to bromine. Notice the endings. When it was an element, I called it chlorine, but when it was bonded to sodium, I called it chloride. As an element, the halogens end in INE, but as compounds, they end in IDE. It's the same here for bromine. When it was part of a compound, it was ending in IDE, but when it was an element, it ends in INE. We look at another example. This time I've got bromine and lithium iodide. Bromine is the halogen by itself. It is more reactive than the halogen in the compound, so they're going to swap places. That means on the right-hand side, I write iodine by itself, and lithium is now bonded to bromine. Again, it's bromine by itself, bromide in the compound. Iodide in the compound, iodine by itself. We look at another example, chlorine and potassium iodide. Chlorine is the halogen by itself. It's more reactive than the halogen in the compound. They swap places, iodine by itself, chlorine in the compound as chloride. In the last example, I've got bromine by itself, chlorine in a compound. Bromine is less reactive than chlorine because it's below it in the group. That means it cannot take chlorine's place and no reaction occurs. As well as being able to complete these reactions, you also need to be able to describe what you will see. For each of these reactions, you are going to see a colour change. The halogen that's by itself determines what colour the reaction is going to be. At the start of the reaction, chlorine is by itself, so it determines the colour. At the end of the reaction, bromine is by itself, so bromine will determine the colour. In the previous video, we looked at the colours of chlorine, bromine and iodine. We saw that chlorine was green, bromine was brown and iodine was purple. When you're carrying out these reactions, you're carrying them out in solution, so you're carrying them out in water. And when you dissolve these halogens in water, their colour becomes lighter. Chlorine is green, but when it's in solution, when it's dissolved in water, it looks colourless. Bromine is usually brown, but mixed with water is going to be orange. And iodine, which is usually a dark purple or black, when it's in solution, it's going to be purple. As I said, the halogen by itself is responsible for the colour. So on the left-hand side, chlorine is by itself, so the solution will start off colourless. On the right-hand side, bromine is by itself, bromine is orange in solution. So you are going to see a colour change from colourless to orange. The next one, bromine's by itself, that's orange, going to purple for iodine, so you're going from orange to purple. Chlorine by itself, colourless, going to purple for iodine. And the last reaction, because the reaction doesn't occur, the reaction starts orange and remains orange because no reaction occurs. These are all called displacement reactions, and we're going to have a look now at some questions, common exam questions on displacement reactions. The first one I'm going to come to is here. You're reacting bromine and potassium acetate, and they've asked you to complete the word equation. Bromine, if you look at your periodic table, is above astatine. So here's bromine, here's astatine. That means bromine is more reactive, and that means bromine can take the place of astatine. Astatine is then going to be by itself. So remember, it's acetate, part of a compound, but it's astatine by itself. And then potassium is going to be bonded to bromine, and that will change the bromine to bromide. So you're just completing that word equation to pick up 2 marks. In another question, they ask you to say what you'd see in this reaction. So in this case, they've given you the symbol equation, but they've written it in words above. Chlorine reacts with potassium iodide to form potassium chloride and iodine. This is an example of a displacement reaction. You start off with chlorine by itself, you end up with iodine by itself. Chlorine by itself in solution is going to be colourless, and iodine in solution is going to be purple. So you get a colour change from colourless to purple. Explain in terms of electron configuration why chlorine is more reactive than iodine. This is only for 2 marks. Because it's only for 2 marks, you're just going to say chlorine is smaller, or you could say chlorine has less electron shells than iodine, therefore finds it easier to gain 1 electron. So you need to tell me what it is that they're doing when they react. They need to gain an electron. Because chlorine is smaller, it finds it easier to gain an electron. The easier it finds it to gain an electron, the more reactive it's going to be. This reaction here, okay, it tells you that you react hydrogen with bromine and that the reaction occurs quickly. You're then asked here, what would happen if hydrogen and iodine reacted under identical conditions? Using your periodic table, you can see that iodine is less reactive than bromine. If it's less reactive, then instead of the reaction going quickly, you would expect it to go slower. So I would say that the reaction should be slower, and I'm going to explain why. Because iodine is less reactive than bromine. A slightly harder question, back up here, is for a full 6 marks on displacement reactions. And it says, The order of reactivity of chlorine, bromine and iodine can be determined by carrying out displacement reactions. Explain how these reactions can be used to show the reactivity of these three elements. To do this, you're going to need to describe how you would carry out those displacement reactions and what you would see. So I'm going to start off by saying I would add chlorine to. Okay, so for all of these displacement reactions, when we were drawing them out, you always had a halogen by itself, and then you always added a halogen to a compound that contained a halogen. So I had a metal, and then I had another halogen. So I used sodium bromide in one, lithium iodide, potassium iodide. You just pick a metal, and then pick a different halogen. So I'm going to say add chlorine to, I'm going to pick sodium as my metal, add chlorine to sodium, and I'm going to pick a different halogen, bromide. Add chlorine to sodium bromide. When you do, chlorine is more reactive than bromine, so you would see them swap places. So you would see a reaction because they swap places. Because there's a reaction, you're going to see a color change. Chlorine is by itself, so it starts out as colorless. And bromine will end up by itself, so it will turn orange. So you add chlorine to sodium bromide, colorless to orange is what you will see. You could then say, add chlorine to sodium iodide. Again, chlorine is more reactive than iodine, so again, you're going to expect to see a reaction. You'll see a color change from colorless to purple. Because both of these reactions went ahead and you saw a color change in both cases, you can then conclude that chlorine is more reactive than bromine and iodine. So you've established that chlorine is the most reactive of the three. You now need to do one further test to compare bromine and iodine. I'm going to say add bromine this time to, I'm just going to stick with sodium iodide. Bromine is more reactive than iodine, okay? I know this because I've got my periodic table in the exam and I know that they get less reactive going down the group. Add bromine to sodium iodide. Again, you're going to see a color change. Bromine starts off as orange and it will turn to purple. This tells me, the fact that there was a reaction, I saw a color change, this tells me that bromine is more reactive than iodine. So my overall reactivity from my experiments, I've got chlorine, which is more reactive than bromine, which is more reactive than iodine. So for each one, you're going to need to say what you would add to what and the color change that you would expect to see, okay? There's lots of different compounds you could use. Just pick any metal. It doesn't matter what order you do the experiments in, but just try and give 3 relevant reactions and their color change, and then use those observations to give an overall trend in the reactivity. So chlorine is most reactive, then bromine, then iodine. There's one more thing that you need to be able to do on the halogens, and it involves these displacement reactions. You need to be able to take these displacement reactions and write ionic equations for them. And using those ionic equations, you need to explain what's being oxidized and what is being reduced. So this is the hardest part of the group's topic, and I'm going to make a separate video where I go through the writing of ionic equations and then how to use those ionic equations to determine what is being oxidized and what is being reduced. So that will be in a separate video.